Hi everyone, in this video I'm going to summarize how you can use logarithms to isolate a power. So first, at the top here, let's review what an inverse operation does in general. So I have x plus 2 equals 7, x squared equals 7, 2x equals 7, and 2 to the power of x equals 7. I forgot to make this pink. So in each of these situations, we use an inverse operation if we want to undo an operation we see and isolate a variable. So if I have plus 2, the inverse of addition is subtraction. So I could subtract 2 on both sides of this equation, and I would get that x equals 5. If I have multiplication, the inverse of multiplication is division, so I can use division and multiplication to undo each other. So in this example, I could divide both sides by 2. That would help me understand that x equals 3.5. In my third example, where I have x squared, the inverse of squaring something is to take the square root, or the inverse of to the third power would be to take the third root. So I could do an inverse operation here. This one is a little special because with square roots, there are two possibilities. So if I take the square root on both sides, I could get plus or minus the square root of 7. So those are all inverse operations that we have learned in the past. They undo something so that we can isolate a variable. A logarithm you can think of as an inverse if you are trying to isolate a power. So if I have this fourth example, 2 to the power of x equals 7, we need some way to undo that so that we can isolate the x. So I'll come back to this one in a moment, but if our exponential form is, if we put it in words, base to the power equals the argument. So in our example, 2 would be our base, x would be our power, and 7 would be our argument. Logarithmic form takes those three pieces and just rearranges them so that our power is alone. So in logarithmic form, our power is equal to the log base of our argument. So you can think of a log as just telling you what exponent would you need to end up with the argument in your equation. So for example, up here, we have 2 to the power of x equals 7. If I wanted to use a log to rearrange this, I would say that x equals log base 2 of 7. So x would be whatever number we need to raise 2 to in order to end up with 7. And then at this point, to find your log, then different graphing calculators will have different places where you can look them up. But you can type in your log into your calculator and it'll give you the exact power that you would need in order to find that. So for instance, in this example, log base 2 of 7 would be 2.807. So 2 to the power of 2.807 will give us 7. So let's look at a couple examples of when this can be useful. In our first example, a population of fruit flies begins with 300 flies and grows 23% each day. What is the exact amount of time until there are 1,500 fruit flies? So from exponential functions, we know that we have an initial value of 300 If it's growing 1.23%, if it's growing 23% each day, then it has a growth factor of 1.23 to the power of x, if x is in days. And we want to know when this is going to equal 1500. So I have an equation, but my variable is in the power, and I need some way to figure out what number would make this equation true. If I'm working with a log, then before I use my logarithm, the first thing I want to do is I want to do any inverse operations I need to so that the only thing I have in my equation is a base, a power, and an argument. In this example, the 300 is not part of my base. The 300 is multiplied by my exponent. So my first step is going to be to divide both sides by 300 to get myself into exponential form. So if I divide both sides by 300, 1500 divided by 300 is 5, which is equal to 1.23 to the power of x. And now you can see we have a base, we have a power, and an argument, so I can use my logs to isolate that power. So my power equals log base 1.23 of my argument, which is 5. So log base 1.23 of 5 will tell me exactly how long it takes for there to be 1,500 fruit flies. And let's find out what that is. So if I type that in, I'm going to get approximately 7.775 . So in 7.775 days, my fruit fly population should reach 1,500. Here's a second example. The other thing we can do with logarithms is we can create an inverse function. So here I have money in an account over time can be modeled by an exponential function. A of t equals 500 times 1 plus 0.037 all over 12 to the power of 12t plus 1,000. So it looks here like I have an initial value of 500. I have 3.7% growth. It's compounding monthly. And I have this extra $1,000. Maybe there's $1,000 in a mattress somewhere that's not in the account. If I want to write an inverse function, this function as it exists, I can put in different amounts of time and I will find out how much money I have after that amount of time. An inverse function will allow me to put in an amount of money and it will tell me how long it would take to get that money. So it's the same relationship, but I'm using, instead of putting in time and getting out money, I can put in money and I will find out the time. So if I want to use logs to rearrange this, my goal is to isolate that t. So let's write this with y and x first. Y equals 500 times 1 plus 0.037 all over 12 to the 12x. And then to get my inverse function, I'm going to swap the x and the y. See if I can isolate y. Oh, I forgot the plus 1,000, plus 1,000. So I cannot use my log yet because I don't have base power argument. So I'm going to do what I need to do to get things in that form. So first step, let me subtract that 1,000. Now I've got x minus 1,000 equals 500 equals 500 times, here's my base, 1.037 all over 12. So that blue section is all my base, and then my power is 12y. So I almost have base power argument, except I still have this 500. So let's get rid of the 500. We'll divide both sides by 500. Now I have, even though it's a little messy, I have an argument, x minus 1,000 all over 500, equal to a base, 1 plus 0.037 all over 12, to a power, 12y. Since I have base power argument, I can rearrange with my log. So my power equals the log base 1 plus 0.037 over 12 of my argument. Now I almost have gotten y alone, but I have that 12 in front. So after this, what I'm going to do is I'm going to divide, or let's write this just to keep it a little simple. Let's write this as I'm going to multiply both sides by 1 over 12. So then we have our inverse function. The inverse of my original is, I'll put this in terms of x. So the inverse function of a is 1/12 log base 1 plus 0.037 all over 12 of x minus 1,000 all over 500. Kind of a messy equation, but this would be the inverse of what we began with. And then we could plug in any value of x, so any desired amount of money. I could put in $3,000 into that inverse function. It would tell me how long I need to wait until I have $3,000, or $10,000, or $700, or $750.83. So no matter what I want, I could put it into that logarithmic function, and it will give me the amount of time needed to get there. But ultimately, logs always come back to this basic thought. A log is just a way of rewriting an exponent in order to isolate the power.